Thank you, everyone, for being here today. We wish to acknowledge this land on which the Physics Institute operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. We welcome Professor Edward Thommes to the seminar today. Dr. Thommes is part of the Modeling, Epidemiology, and Data Science group at Sanofi Pasteur Global, also an adjunct professor in the Department of Mathematics and Statistics at University of Guelph, as well as York University, and an affiliate member of the Waterloo Institute for Complexity and Innovation. He started working in the industry in 2012 and holds a PhD in astrophysics from Queen's University in 2000. His research interest includes biomathematics, epidemiology, earth economics, the conduct of real-world evidence studies, artificial intelligence, and machine learning. Dr. Thommes will be presenting his research titled From Planets to Population Health. You're welcome to present, Dr. Thommes.
Thank you very much for the introduction, and thanks for the kind invitation to speak to you all. So for this talk, I was asked to kind of talk a little bit about, my things that I've done in the past, career path, education path, and so on, going, further back than industry where I am right now. So I've tried to kind of meld together the two, and as you just heard, my original background is actually in astrophysics, not in epidemiology. I'll sort of try to draw a connection, however tenuous it may be, from the stuff that I started out working on to what I'm working on these days. And the unifying theme, as you might guess, is modeling. Oops. Let's see if my slides advance. Yes, and I should, by way of disclosure, I am an employee of Sanofi. I used to be able to say Sanofi Pasteur. That's the vaccines part of the company, but now we're all one uniform company. Dropped the Pasteur. And so some of the research, not the astronomy stuff, you may guess, that I'm going to talk about was or is financially supported by the company. So a little bit about myself, a little bit more about myself and where I am and what confusing combination of things I am or I'm doing. So physically, I am here in Canada. Specifically Guelph, next to the University of Guelph. My day job, though, is as you heard, in the modeling, epidemiology, and data science team of Sanofi Pasteur, and that's part of the global operation, and that the global vaccines part of the company is actually headquartered in Lyon. So that's the first picture you see here. That's the Planetary campus in Lyon, where the vaccines headquarters is. Now, I, since COVID, like most people, I haven't done much traveling, so I actually have not been there. In fact, I haven't even been at the Canadian site since then, which is the North York site, very close to York University. And actually, that's not quite true. I was there one time because my laptop needed some fixing. I had to have special dispensation to get in there, and I was scanned by an infrared scanner to see if I had a fever. And the other two affiliations that I have are University of Guelph and University of course, York University, where I'm adjunct in the math and stats departments in both cases. So anyway, that was just the pictorial representation. Now, physically, my career path is a little bit maybe unconventional and in various different directions. So my PhD was from Queen's University in astrophysics back in 2000. So that's where I started out. And then I did a number of postdocs after that at UC Berkeley, and right next door to that at the NASA Ames Research Center, which is like at the south end of the San Francisco Bay. Right next door to Google, actually, although back when I was there, Google was just like a small 2-story office building, which tells you how old I am. And then back to Canada, where I was at University of Toronto for a bit, at the CITA, the Canadian Institute for Theoretical Astrophysics. And then I went back to the US. I was at Northwestern University, and then finally I came back to Canada and was a researcher at University of Guelph for a while. And that's when I went into industry then. So I was at GlaxoSmithKline at GSK from 2012 onwards. And then I had a sort of a shorter stint at Takeda, Canada. And then I went back to the US to Sanofi Pasteur, it was still called back then, in Swiftwater, Pennsylvania, which is the US vaccines headquarters and a very big manufacturing site where they make all of the flu vaccine for North America. And, oh, I guess that's the last thing I had. So the last part that's not on here is then I once again came back to Canada, and I'm now with the global part of the company, although again, I'm physically based, back here. It's a lot of back and forth, both in terms of what I was doing and in terms of geography. And like I said, the sort of unifying theme, or the one that I'm going to try to shoehorn everything into, is computational work, modeling. And there's sort of a couple of overarching wisdoms that I think we generally look to, whatever the field may be that we're doing, our modeling in. And of course, we've all heard all models are wrong, some models are useful, from famed statistician George Box. Another popular one is Albert Einstein. A model should be made as simple as possible, but no simpler. So, sounds very simple when you say it, but of course the art is in how you actually do that. How do you decide when you've done the right level, reasonable level of abstraction in your modeling, that you're, you've simplified it to a point where you can actually extract insights out of it without having thrown everything but the kitchen sink at it. But on the other hand, you haven't simplified it so much that you've lost some of the important dynamics, some of the important moving parts. Okay, so the first part, I'm going to take the opportunity to take a bit of a trip in the Wayback Machine and talk about some of the things that I worked on in astrophysics. So my area was planet formation. There's a really nice artist's rendition here of what the early stages of a planetary system might look like. And so just a little cartoon version of what all of this, how all of this shakes out. So for star and planet formation, we start out with these giant molecular clouds, hydrogen and helium clouds out in space that, become sufficiently dense somewhere in some part of them that they start to undergo runaway gravitational collapse. Eventually, they collapse to a high enough density that a protostar starts to form, and a disk starts to form around that. And the disk is just because, whatever clump of molecular cloud you collapse, it'll have some sort of slight residual angular momentum, and that's then, that determines the plane that the disk points or lies in. So that kind of goes on for a while. Usually you have these nice, very spectacular jets that come out the top and bottom of the protostar. And you have the sort of the envelope around all of this dissipating, and you have more and more of a well-defined disk. And then this is where the interesting stuff, well, planet-wise, the interesting stuff starts to happen, because parts of this disk start to condense. Well, really in detail, what's happening is little itty-bitty grains are hitting each other and becoming bigger grains and becoming pebbles and becoming boulders. and gradually accreting each other to make bigger and bigger stuff, eventually getting up to something the size of the Earth or Venus. And then on the upper end of the scale, some of these cores, some of these solid bodies then form the cores onto which some of the remaining hydrogen and helium gas in the disk condenses onto, or gravitationally collapses onto. And that's how we get something like a Jupiter or a Saturn, a gas giant planet. So they're basically like a little sun with a core that isn't high mass enough to actually undergo fusion. And then Uranus and Neptune, our outermost giant planets, are, we think a kind of, abbreviated version of that, something that just got to the point of starting to accrete gas, but then ran out of gas. And then finally, after, the end of all of this, up to, billions of years later, 4.5 billion years in our case, we end up with this sort of, more or less regular looking planetary system, although as we'll see in a moment, a lot of the time not quite so regular. All of the gas is gone a long time ago and we're just left with the planets. Couple of useful physical quantities to keep in the back of one's mind when dealing with planetary systems. So there's one astronomical unit, is just the radius of the Earth's orbit. And for scale, Jupiter has a radius of 5.2 astronomical units. Saturn is about twice that. And Neptune, the outermost giant planet of our solar system, I guess now the outermost planet period, is at 38. And on the mass scale, one solar mass, the mass of the sun, is 2 times 10 to the 30 kilograms. One Jupiter mass is of order 10 to the 3 that, so a thousandth of that. And an Earth mass is 1,000th, again, roughly, of a Jupiter mass. So that's just sort of to give you a rough idea of the scales. And now jumping right into planets around other stars. So until 1992, all we knew about was our own planetary system. And now we figured it would be really weird if there was only one that ever formed. So there must be lots of them out there, but we've never actually seen one until the discovery of 2 planets orbiting a pulsar, which is kind of an extreme case of a planetary system, but because of the properties of pulsars, it was actually easiest to detect, or basically these were the easiest to detect ahead of all of the other ones that were eventually found. And soon thereafter, relatively soon thereafter, more normal-ish planets started to be found. So in 1995, October of 1995, Michel Mayor and Didier Queloz announced the discovery of a planet orbiting a star called 51 Pegasi, and they shared the 2019 Nobel Prize in Physics for this remarkable discovery. And the technique that they used, and the one that was also used for the original pulsar planets, is to look for the radial, the radial velocity component of the motion of the central star. So of course we know, from classical mechanics, that if you have 2 things orbiting each other, something like the Jupiter orbiting the sun, it looks like the sun is stationary, but in reality, of course, the 2 are orbiting their common center of mass, which does mean that the sun moves a little tiny bit. And if you have super precise spectroscopy equipment and techniques, you can actually find the Doppler shift associated with the radial component of that. So the component of that motion that goes away from us and then comes back towards us. And that gives you not the mass of the star, but not the mass of the, shouldn't have written star, not the mass of the planet, but the mass of the planet times the sine of the inclination relative to us. The other technique is to look for eclipses. So it's called transit photometry. So you look at the light coming from the star, and you have to monitor a whole bunch of stars at once for this to pay off. And you look for very, very slight dimming and then brightening again of the star. And you have some very exact or precise things that you're looking for that are signatures of, this happened because a teeny tiny planet passed in front of the star, rather than this was, sunspot activity or something like that. And so to date, close to 5,000 exoplanets have been discovered in 3,670 planetary systems. And the number of systems is smaller than the number of planets, simply because a good number of planets are actually in systems of more than one planet. So 813 systems that have been found have more than one planet, which can mean 2 planets, 3 planets. I don't know what the most is that's been found so far. I think 4 or 5. And I should say that to date, at least with the radial velocity technique, most of these tend to be on the bigger side. So they tend to be, well, they're all actually bigger than the Earth. Basically, the more massive they are, and the closer they're orbiting to their host star, the easier they are to find. Check how I'm doing on time. Okay, so with that, well, I guess we're still in the preamble, actually, because you can, I guess the obvious question then to ask is, with all of these planets that have been found, how do they compare to the solar system? Because, before we ever saw any other planets, the obvious assumption to make was that we are probably a very ordinary, very average, very boring example of a planetary system. And it turns out not to be quite that simple. Now, the very first exoplanets that were found were very different. These were all gas giants and generally more massive than Jupiter and Saturn. And that was one thing right there, that the first planets that were discovered had a mass, or a minimum mass, because there's the sign I in there, that were quite a bit bigger than Jupiter. So we were finding these very big gas giants. They were very close to their host star, in some cases closer than Mercury is to the sun. And in many cases, their orbits were very far from circular, so they were very eccentric. And here's a semi-major or mass, Jupiter masses versus semi-major axis plot of, I don't think this is entirely current, but this is a lot of the exoplanets discovered to date. And this is for comparison to 4 giant planets in our solar system. You can see that there's a whole bunch of stuff here that doesn't really look like us. Now, in public health and epidemiology, and we deal a lot with bias, right? In this case, also, there are some extremely strong biases at play, which is simply that massive planets and planets close to their host star are easier to find than through this radial velocity technique, and also through the looking for eclipses technique, than things that look more like Jupiter and Saturn. So there's a very strong bias effect that made us find the weird planetary systems and planets first. Now, mind you, these radial velocity and eclipse searches have been going on for long enough now that we would have expected this part of the parameter space to fill in a little bit more. That's where, the puzzle sort of starts to get, the plot sort of starts to thicken. Let's see, the other thing, whoops. Oh, that's threat protection. That's not good. Oh, here we go. Okay. The computer is doing odd things. Okay, and the other thing I mentioned, the eccentricities. So the eccentricities of our planets are pretty close to 0. So they're very nearly circular. And around other stars, there are a lot of quite eccentric planets. Another mystery. Let's see, do I have time to talk about this? I guess, yeah, I'll say a couple of words about this. So if you're doing these, these sort of simulations that are done in a lot of astronomy applications, and not just when you're looking at planets, also when you're looking at things like galactic dynamics although I guess this particular one more for planetary systems. You have to worry about, well, basically you're solving, I mean, a lot of us have dealt with agent-based models, right, in this or that aspect of epidemiology, disease models, or even, population models. And these so-called gravitational n-body simulations are basically a special case of an agent-based model, where the individual pieces, they don't have any, well, agency, so maybe it's not quite correct to say agent-based, except that, they follow the laws of physics. So you have particles, they each have some mass, they they interact via gravity, and throw them into your simulation and see what happens. Now, the problem is when you are looking at something like a planetary system, say you're trying to look at stability of planets in the solar system, and you want to see, if you go forward in time, how many billions of years does it take for Pluto to get ejected from the solar system, or does it ever? Now, the problem is even the fanciest differential equation solvers will eventually, error will eventually accumulate, and you'll see your Pluto ejected out of your solar system, but you won't know whether it is something that actually would have happened or because it happened due to numerical instability. And so one of the very clever, well, really the very clever way that people came up to solve that problem, to be able to integrate one of these systems, solve one of these systems over a time scale of actually billions of years and not have to use prohibitively small time steps, was this thing called symplectic integrators. And the idea is you don't try to solve the equation, the gravitational n-body equation exactly, rather you try to solve exactly solve a problem that's adjacent to it. And you have the system flip back and forth between two states. So you have your system of multiple, say, planets, and you go for part of a time step, everything evolves on perfectly Keplerian ellipses, as if they were all in their own system with no other perturbations. So you do that for, say, half a time step. Then you add up all of the interaction forces amongst all the planets, so they all get like an instantaneous impulse. They all end up on slightly different orbits, and then you evolve those orbits. And it turns out, so you're exactly solving not exactly the right problem, but the nice thing is your error is bounded when you do that. So this was a very, sort of a breakthrough innovation in this field. Okie dokie. So getting back to this theme of, why do a lot of these planetary systems seem to look more disordered and not as like nice and circular and relatively low mass, in a relative sense, as our own. And, repurpose a few quotes from famous people in this talk with probably varying degrees of success. There's this weird sort of uncharacteristically bloodthirsty quote from former UN Secretary General Boutros Boutros-Ghali, where he said the best way to deal with bureaucrats is with stealth and sudden violence. And the theme that emerges from some of the work that's been done and some of the stuff that I've worked on is maybe the same thing applies to planets. And then this raises the question, if there are so many planetary systems out there that show evidence of, fairly violent things that caused orbits to, become eccentric, caused orbits to become a lot smaller than they probably were originally, is the solar system really completely average, or is it a kind of a example of, is it in some way special? And, we hate to say that, right? Because, that, we don't want to think of ourselves as, we don't want to think of there being something weird about the solar system. But anyway, we have to ask the question. And as we'll, to sort of foreshadow, we'll see that, we're still, we're not as average as perhaps we think we are, but we're still one in an ensemble of many similar things, very likely. I think I'm going to skip over this next part, except to say that, if you want to do simulations of the whole shebang, not just gravitationally interacting planets or masses, whatever they may be, but also the gas that exists in the early stages of the planetary system. You know, you have some prohibitively expensive you know, computational tasks to solve. And people have done these hydrodynamic simulations, but you can only go for a relatively short amount of time. You can't go for the approximately, you know, few million years up to 10 million years of simulated time that we believe, and we can see actually that the planet formation, the early planet formation process goes. And so long story short, with some collaborators, I worked on a model that kind of is a compromise between like a full hydrodynamic model and just an n-body model. And so we, and this came out way back in 2008 in Science, where we tried to kind of do big picture simulations of how all of these pieces fit together. And the compromise that we had to strike was to represent the gas disk in which all of this is happening as like an azimuthally averaged thing. So we're not resolving all the individual detail, we're simulating it as a bunch of rings, and then calculating the forces between the rings and the planets and the viscosity by which the the gas itself evolves. And so these I'm going to show a couple of movies here, and they're a little bit busy, and I tried here to explain what the movies, what all the different things labeling the movies are, and it's still a little complex here, but basically the round things are the protoplanets, or little protoplanets that gradually grow bigger. The light blue stuff is the gas disk density, rather the surface density, the total amount of gas you encounter if you go in a column through it, averaged around, azimuthally averaged around, all the way around 360 degrees. And then we have, so this is the scale for the disk density. This is the scale for the eccentricity, so how, for the planets, so how far away from circular they are. If they're all the way down here, they're on a circular orbit. If they're all the way at 1, that means they've just been ejected. We also have the inclination here, but let's ignore that for the time being. And we're really looking here at larger things. So we're looking at things that are gas giants or could potentially become gas giants. And so these things are, they consist of 2 parts. They consist of a core, which is the white part in the middle. This is the thing that grows kind of like Earth or Venus. And then they have a gas envelope, which they accrete from the surrounding gas. And you have equations to model all of these things. And then as the movie runs, you'll see these numbers change as they grow bigger. Both the solid part grows bigger and the gas part grows bigger, and you'll see the surface density evolve. And okay, I guess I've sort of skipped ahead to the punchline, but that's okay. So the problem is, I mean, we don't, in this field, we're always looking at things that are very far away, and we're trying to infer things that happened a very long time ago. So we often don't have very strong constraints on what are actually, the initial properties of one of these planet-forming disks. We see different snapshots at various times, but of course, because the process takes millions of years to play out, we can't, sit down and watch the movie for ourselves. We just see different frames of the movie at different times. So we think that the initial masses of these disks are somewhere between, a few hundredths to a tenths of a solar mass. We think that the viscosity of the disk lies in a range of sort of 10 to the minus 3, or a few times 10 to the minus 3 to 10 to the minus 1. In this, parameterization, this alpha parameterization, which, I'm not going to go into, but basically higher alpha is higher viscosity. And so you can run as we did here, we ran a bunch of simulations in different parts of the parameter space, and we looked at how the planets evolved and what you ended up with in the end. By in the end, we mean once the gas was gone. And so this, I guess, is where we start the movies. So we have this region down here, and again, you probably have to squint to see this, and maybe you can't quite see it, but this is, you can just see from lack of these blue envelopes. Here we don't form any gas giants in these simulations. In this part of the parameter space, we form quite a few gas giants, and they tend to migrate a lot. Their orbits tend to shrink a lot, and sometimes they get pushed all the way into the central star before the gas is all gone. And then there's this kind of diagonal region here in the middle that is somewhat intermediate. And so this is where, yeah, and if you think of it in terms of timescales, this is where, so here in this region, because you have a lot of gas to work with and a lot of solids to accrete, things happen faster. And so the time scale to form a giant planet, something like a Jupiter or bigger, is less than the lifetime of the disk. So tau giant is less than tau disk. The opposite is true down here. So a giant planet takes longer to form. By the time it would have formed, it's already too late because all the gas is gone. So no Jupiter, no Saturn. And then in between, you have this region where the two timescales are kind of comparable. And if we look at a couple of examples, so this is in the not so much with the gas giants regime. Good. Okay. So what you can see here is you can see the surface density of the gas going down. So what's really happening, and it's a bit distasteful, but picture a toilet. Picture the water going down the drain. That's basically what the gas disk is doing. Because of its viscosity, it's the individual gas parcels, I guess, are spiraling inward and ending up feeding the central star, and that's how the disk goes away. And while all of this is happening, inside of that disk, which consists of both gas and solids, little rocks and boulders and stuff, all of the planet formation is playing out. In the end here, you see you end up with things, you do end up with things that are bigger than an Earth. These are Earth masses here, I should say. And some of them have somewhat of an envelope, but nothing formed that is, everything that formed here is basically smaller than an Uranus or Neptune. This is this is again the low mass disk. Whoops. This is the higher mass disk, higher viscosity regime. This is an example. And so here, everything happens faster. By the way, you can see these cores getting bigger, and you can see them trundling inward as the gas basically carries them along. And you can see these gaps forming in the disk, which is basically the planets and the disk effectively, as they gravitationally interact, they effectively repel each other, which has the effect of the planets opening an annular gap, sort of an inverse donut in the gas disk. And so in this case here, we end up with a single very massive planet that's about twice the mass of Jupiter. A bunch of stuff here has been removed at the inner edge, although some of that, some of those might in reality still be around, but we won't get into that. It's the same one again. And now finally, what about this intermediate regime here? We run an example of that. So this is sort of in the middle. So things are happening, things are migrating. They're starting to accrete, some of them are starting to accrete gas. The disk is, draining away all the time, all the while. And you can see now, these planets are getting big on a time scale not that different from the gas going away. And so by the time the gas is, almost gone, like it is now, you have a number of gas giants, not insanely big gas giants. They're not on terribly eccentric orbits, at least these guys, meaning, they're towards zero here. Some of these are more eccentric, but there are other ways that could be dissipated later on. And you end up with, and there's a certain degree of cherry picking, of course, that goes on, but you do end up with a typically along in this diagonal region that I was just showing, systems that look more along these lines, that have a couple of gas giants. They're not all deposited on the central star, and they do still have overall somewhat lower eccentricities. And so you can see where this is going. So the argument then is that, oops, too far. The argument then that we made is that it's this region in the middle, this sort of transition region, that is the one that is most likely to produce analogs to our own solar system. So kind of you've heard of the Goldilocks zone around stars in terms of, the temperature is just right for liquid water on the surface. This is a sort of a meta Goldilocks parameter space of protostars and protoplanetary disks that is more likely to form something that looks like our planetary system. And I guess I've probably gone a little bit, I gave a little bit more time to the astrophysics than maybe I'm shortchanging the other stuff a bit. So I think I'd better go on to the next part, which is the population health. And I apologize for this, by now, I think, quite terrifying picture of somebody sneezing. I mean, this was disturbing even before COVID, and now it's like 10 times more disturbing, but I guess it kind of gets to the heart of what we deal with in infectious diseases. So to kind of try and make this connection, so all this, celestial mechanics and astrophysics stuff, of course, can be quite involved and computationally and theoretically challenging. But dealing with epidemiology and and trying to model that has its own difficulties and its own set of complexities, as we know. And to compare and contrast the two, we know through bitter experience that epidemiological modeling is messy. Compared to the astronomy stuff I was just showing, biological processes are way messier than physics. We know that real world data, claims databases, or even the certainly the surveillance data that we know and love for flu and RSV and now COVID, is messy and subject to all kinds of biases and changes in reporting practices, et cetera, et cetera. And of course, all of this has underlying it human behavior, which we know is extremely messy and all over the place, and has a tendency towards the irrational, sometimes very irrational. But there are also things about it that make it easier, at least compared to the stuff that I was just talking about. So with these sorts of, if you're dealing with epidemiology, you definitely do not need to take a system and evolve it for 1 million years. Interested in timescales that are of interest, to a human life. So that's kind of the longest timescale we generally deal with. And the messiness is actually a blessing in some ways, because, when, like I was alluding to, when you're doing with the symplectic integrator, or when you're doing these sorts of astronomical, in-body calculations, for example, you're always obsessing about, am I using the right ODE integrator? Should I use an adaptive time step? Am I using this symplectic integrator correctly? Are there too many close encounters? Blah, blah, blah. When things are this messy and stochastic, there's not really any point in obsessing, with individual simulations, whether your solution is exact. You really have to run large ensembles anyway. The other thing is, in a lot of, these sorts of simulations, especially ones that go over longer times, you have to worry about numerical instability. I mean, we've probably all run into various annoying and unpleasant examples of that. But the thing is, with epidemiology, you're fundamentally dealing with human beings, which tend to come in integer numbers. And, lo and behold, when you're dealing with things that are quantized into, integers, numerical stability isn't usually a problem. So that, and it took me a while to get my head around that when I started to go into this field. Sort of let go of, an obsession of, oh my God, I have to use an adaptive time step, and I have to, this model has to be, have a time step of like a small fraction of a day, because, used a different time step that it was believed reproducible. Not as important anymore in this. I mean, you still have to pay attention to it, but it's not as central in some ways. Okay. Okay. This part I'm probably going to just essentially skip over. Well, maybe not entirely, because it does actually bear on all of this. I mean, we've been talking about bias, bias in astrophysical observations of extrasolar planets, and of course we know there's tons and tons of bias in health data and any type of real world data. One particular thing that I worked on is, you might have heard of Sanofi's high dose vaccine for 65 and up. And so there were these trials run, or this trial run back when the stuff was pretty new, in US Veterans Affairs centers. And they tried a high dose vaccine versus standard flu vaccine. Some of the veterans were all like 65 and up. And I mean, right there is a bias, because if you're talking about military veterans, you know, it's definitely a biased population. For one thing, they are predominantly male. But then the disturbing thing, and certainly disturbing for the folks that I worked for, was that the study found no significant benefit to high dose vaccine compared to standard dose vaccine. And in a follow-up study that we looked at this and found that there was a significant bias, what we would call prescribing bias, going into this, which is that the people that received high dose vaccine, and this is back when, you know, there was not nearly as much of it around in the US as there is now. So some of this, you know, the centers were usually being supplied with significantly fewer doses than they had people. And so the nurses and doctors that were administering this were tending to, it seems, they were giving it to a population that ended up having, you know, in the previous season, having a significantly higher higher rate of severe outcomes of influenza-associated pneumonia, specifically. And so then the question is, why is that happening? And what seemed to be happening, you know, and this is happening even after, you know, there was controlling for all of the, you know, patient characteristics insofar as was possible, or as was observable. So what seemed to be happening is that there was some sort of triaging going on, whereby healthcare providers were preferentially giving the vaccine to patients who were more frail. And the reasoning presumably being, well, you know, they needed more protection. We only have so many doses of this stuff, which is supposed to be better. So let's give it to the people who are most likely are at highest risk of getting, you know, a nastier flu-related outcome this season. And sure enough, once you tried to control for that using a sort of ratio of ratios methodology, we did actually find the expected relative effectiveness of high-dose vaccine, which is that it's about 25% more effective than the standard dose for senior citizens. But then there were, okay, so this is, I guess this gets a little bit esoteric, but then there were some additional, you know, concerns about this method that we used, which is called the prior event rate ratio method for correcting for this bias, that itself could be subject to bias and itself might be kind of spoofed or might not work as intended if there were certain associations at work. And anyway, so this gets into the realm of causal diagrams and trying to you know, write down basically all of the causal associations that could be at work somewhere, and then trying to, you know, anticipate what they might be. And I guess I really don't have time to go into the details of this, except to say that Bayesian networks are quite fascinating and also can hurt your brain if you think about them long enough. But anyway, to skip to the punchline, I'm not sure it's actually the punch, even a punchline, but you end up doing, the approach here was we don't know exactly what the biases are in the system, but we can put limits on them. And so you can do this thing called probabilistic bias analysis, where you kind of draw, you have a posterior distribution of what could the possible biases be. You draw from them and you do all your, calculation of what must be the correct, the intrinsic actual effectiveness, relative effectiveness of high dose, given what it is that you actually measure at the other end. Explained this in a lot of detail, I realize, but I should probably get on to the as much as I can do in the last 10 minutes. So other stuff that I have worked on, and you can see this goes back to before COVID, is to model and to also try and forecast seasonal influenza, which is, if you've worked on it, is a pretty tricky problem. We know that flu seasons regularly recur, but the severity and to some degree the timing of the seasons can change a whole lot from season to season. So some of the things that we were starting to work on was taking, and you probably know Julian Areno's work on these hybrid models, and this is the same sort of idea. Instead of a compartmental model for the entire population, you divide your population up into different regions, generally different geographies, and you have versions of this model, or maybe a slightly more complex, like SEIR model or what have you, running in each region. The regions are coupled together. People can go from one region to another, and then you get a geographically stratified forecast of how a flu season plays out if everything works as you want it to. And then, we were working on this happily, and then of course COVID happened, and then everybody turned their, everyone was doing modeling, turned themselves towards COVID, as we know. And so this is some stuff that I did with the research group at the University of Guelph. And this is actually an attempt to be sort of more on the simple side of modeling, but at the same time to also make it be something that people can interact with directly. So this is written in R with a shiny interface, so you can actually access this online. And I've put the link here. Or if you want to go to it directly, it's ethommes.shinyapps.io, and the COVID tool. You can put the link in the chat later. And the idea here is to have a simpler model. So it's not even an SIR model. It's something very much analogous to the York, you've probably seen the York COVID Ontario forecast. So this is a similar idea where you use the fact that, we know that incidence is locally exponential. So for a given all other things being equal, you're going to have exponential growth or exponential decay depending on what your instantaneous, effective reproduction number is. And so we can use that to make sort of short-term forecasts in different regions. And, pull this from the Johns Hopkins data. So in principle, you can actually pick any place on Earth that has Johns Hopkins data. So right here we're looking at Canada, and we're comparing Ontario and New Brunswick, which is actually taking off surprisingly well. I didn't realize New Brunswick had this many cases. Anyway, so this was kind of, in a way, a quicker and dirtier modeling exercise, because of course, everybody was sort of working under a sense of great urgency. Certainly in the initial stages of COVID in 2000. And so then some close to time. So since then, also with some of collaborators, also others in the MEDS group and in the University of Guelph and some folks in France. We've kind of been going back gradually to the more complex version of all of this, the geographically stratified version. And in the US in particular, you can get mobility data, which is sourced from cell phones, from people who've opted into sharing their location data. And this particular set of data from a company called Cubic has some advantages over the stuff that Apple and Google, as you probably know, are published for free, or published freely available ever since, I guess, spring of 2020. Because this is kind of a more direct probe of the thing that we actually care about for epidemiology, which is the contact rate amongst people. And also it has in it a flow of people from one geographic region to the next, in this case at the county level, which the Google data very much does not. The Google data, as you may know, is just a local sort of index of relative activity, people in the workplace, usage of transit, people using parks and so forth. But it doesn't give you, it's a scalar, but not a vector quantity, right? So it's not giving you anything about how at what rate are people traveling from here to there. And so we've been working on this and some stuff with it. And it's sort of an initial step of how do you actually use this with an epidemiological model and with forecasting. You can ask the question: are the divisions in which we're given, are the geographic divisions that we naturally work with, because they've been made for us, states and counties, are these really the most sensible ones to be using from an epidemiological point of view? So, some work that we have going on right now is to use this flow data and to try to use, a fancy machine learning algorithm, to use the technical jargon, which was the brainchild of Mihai Nica, who's a professor in the math and stats department here at Guelph, to try and partition these counties into clusters of counties that are kind of act dynamically as one that are well mixed with each other, but less well mixed with adjacent clusters. And so there's sort of an iterative process by which you try to identify these regions. The idea being, once you've identified these clusters, you can then consider each cluster to be one, more or less epidemiological coherent region, which then allows you to do these sort of geographically stratified models in perhaps a more sensible way than if you just go in there and chop everything up along state or county lines. What else do we have? You can also use this data for something else, which is, so what I just talked about comes from the geographic flow, the location to location flow. You can also use something else in the data, which is a proxy for contact rate, which, like I was saying, that's the thing we really care about, because the contact rate is what translates into the rate of transmission. And we can use the contact rate together with the actual observed incidence to try and back calculate things about the per contact transmission probability, which of course is affected by things like mask wearing early on, and later on by, of course, new variants of concern replacing the previous ones, and thank goodness, vaccines. Okay, so I think that was is that my last slide? Yes, okay, good. So I'm almost reasonably on time. Okay, so to tie all this together, or to attempt to, going back to the quotations we had in the beginning. Oops. We had these two. We had George Box, we had Albert Einstein, and then I was trying to find a third one. And not quite sure this one entirely. You know, it's a little bit a tortured insertion into here, but the third one here we have General Patton, famous general from World War II, whose famous quote is that a good plan violently executed now is better than a perfect plan executed next week, which is basically a sort of militaristic way of saying don't let the perfect be the enemy of the good. And if you want to try and reword it in modeling terms, you might say something like a good model that you enthusiastically code up right now is sometimes better than a super fancy, parallelized, beautifully commented, beautifully formatted, version controlled model that you code next week, or, well, more realistically, maybe 2 months from now. Now, mind you, that only applies under a very particular set of conditions, which is if you're trying to do something, you're trying to get an insight into something, sometimes it's good to kind of go ahead and, you know, just sit down and do it and get sort of an early toy version of your model running and iterate on that. Of course, when you're actually, you know, submitting your paper and you're putting all the code up on GitHub, then you obviously should do all of these things. You should have, you know, beautifully commented, fully functioning, perfectly error handling code that other people can enjoy and not have crash. But anyway, so on that note, I guess I will stop and take any questions that